Hello, everyone. Today we have here Professor Koyejo, a computer science professor here at the University of Illinois. Professor Koyejo is going to talk to us today about how AI can be applied to the medical field and how it can also be used to help develop treatment plans for long-term illnesses. Professor Koyejo, take it away.
Great, thank you very much. Thank you also to WCS for putting this program together. I think it's a great initiative. So today I'm going to talk a bit about some of my work in AI for healthcare. The title of the talk is Applications and Challenges in AI for Healthcare. More broadly, my research focuses on the foundational work in AI and machine learning. And I also think about various applications to healthcare, but also to other kinds of scientific problems. And today I'm going to just give a bit of a snippet into some of the things that we work on. So if you're not familiar, broadly, AI is the science of developing machines that can learn from experience to solve real-world tasks and real-world problems. And among these problems, I think one of the more important ones is applications to healthcare, because I think healthcare is perhaps one of the most impactful potential application areas. You can think of various applications that are already being explored that try to work on triage and treatment recommendation, surgical planning, drug discovery, and many, many more applications of AI. Today, I'm going to talk briefly about two applications that we've worked on in the lab. Mostly, I'll focus on imaging-related applications. I think I could talk about them easily with pictures, so we'll focus on those. In pre-surgical planning and higher-risk radiological imaging. And then maybe to give a somewhat broader flavor, I'll talk a bit about challenges that I think are interesting in how we bring AI to medical applications. So I'll think about privacy, and I'll think about trust, and I'll tell you a bit about some of what we're doing in those areas. So first, I'll talk about pre-surgical planning for glioma segmentation. So before a surgeon operates, they have to plan the operation procedure. And this planning is extremely important when you have highly invasive procedures. For instance, if you're doing brain surgery. And so in collaboration with OSF Healthcare and also other professors at University of Illinois, we've been working on pre-surgical planning for gliomas, which are brain cancers. So the data that is collected looks something like this. You may have seen versions of stuff like this before. This is an MRI of the brain. So this is magnetic resonance imaging measured in these big magnets. And taking this image, the surgeon has to decide what exactly the surgery is going to do. In particular, they're looking for where the cancer is and sort of where to cut and what happens. Cut in such a way that it has minimal effect on the patient afterwards. However, there's a lot of evidence that looking directly at MRI images can be challenging. You might have already imagined this from looking at what I showed in the pictures earlier. There's a better process that we've been working on, which is based on VR. So we're creating pre-surgical planning in VR, so the surgeons can go in and in VR sort of look at 3D maps of the brain. They're able to navigate easily in all 3 dimensions. And now there's lots of examples of initial plans made in MRI that were refined after looking in VR that led to better outcomes for lots of patients. And so there are several components of getting this to work. I'm going to talk about a little piece, which is where some of the AI comes in. But again, this is sort of much richer, broader set of questions. The AI piece is in segmentation. So segmentation nominally requires that the surgeon or some other trained professional spend many hours looking at slices of the brain and mapping out exactly where the brain cancer is. Now, this is a task that machines can be very good at. And you can think about this, the lingo is a classification problem. So the job of the AI model is to predict a label for every region of the brain, whether it's a tumor or progression or versus not. And so here are some examples. I'm showing an example for a prediction of tumor core, the ground truth, which is the true label for this patient versus our prediction. You can see similar kinds of results for instance, the label of enhancing tumor, showing what this classification looks like. So here's an example of AI model that's part of an entire pipeline to improve surgical planning. I'll talk about some other examples. Here's another task that we've been thinking about related to higher risk radiological imaging. So this is in collaboration with great collaborators at DuPage and also here at Illinois. And here I'll talk about low-dose image reconstruction. So X-rays and CTs, as ubiquitous as they are, they're taken all the time in hospitals. They can be risky for very sick patients because the way the imaging works, you have to send lots of radiation through the body. And if the patient is high risk, they might not be able to handle high radiation. So one approach to reduce the amount of radiation is just do it directly. So you can send lower amounts of radiation through the body. The issue that happens is that if you send lower amounts of radiation, you end up with much blurrier images. And so it's harder for the radiologist and the doctors to tell exactly what's going on in the body. So here's an example on the left of a low dose image. And as you can see, it's blurry, it has noise, and it's hard to tell exactly what's going on. I'm showing in the middle, this middle column, are results from our model. So we built a deep learning model that takes the low dose image and predicts the image as you would have seen it if it was collected at high radiological doses. As you can tell, if you compare it to the image all the way on the right, which is the regular image, it's virtually indistinguishable. So we get sort of all of the details right. And so this is important because now you can image patients that are too sick to have the full dose, yet still be able to get high resolution images for downstream tests that you're interested in. Just to dig a bit more, you can visualize the performance in a bit more detail. I'm showing patches blown up to show that even in fine detail, we capture most of the fine detail of all of these reconstructions. You can do this for X-rays. We can also do this for CTs. The nature of the noise is a little bit different. The model is a little bit different, but the sort of main task and the main conclusions are similar. And again, if I blow up a patch, you can see that we also get the fine details correct. And so this allows the radiologist to be able to, again, image the body with low radiation doses, but still get the fidelity that they would have gotten if they had imaged at higher radiation doses. From a machine learning point of view or AI point of view, this is image super resolution problem. I'm trying to get an image from a low resolution to a high resolution. It's commonly done in various computer vision tests. And what we've shown here is success applying these techniques for medical imaging. Another interesting application of some of our work is another high-risk radiological imaging task of synthesizing CTs from X-rays. So CTs are important for finding pathologies that may be obscured in a standard radiograph, so in a standard X-ray. The issue is that CTs require exposing a patient to much higher doses of radiation than you would be exposed to in a standard X-ray. They're also more expensive, and in many places they're not available. So X-rays might be available because they're cheaper, where CTs are not available. And so for all these reasons, a useful task is to take X-rays and upsample them from 2D sort of flat images to 3D images. If this can be done successfully, then again, a radiologist can look at the CT. It's much easier for them to understand the pathology and look for any kind of medical issues in the 3D image as opposed to the 2D image. So here's an example of some results from applying a deep learning model to this task. This is a sort of 2D to 3D synthesis problem. And I'm showing on the left an error heat map showing sort of where the model works well and where it seems to do a little bit worse, average down in 2D. And on the right, I'm showing slicing through the image, what the reconstruction versus ground truth on the left, reconstruction on the right look like. And a bit more detail, I'm showing here the original 2D projections, 3D renderings, and both the single slice in 3D and comparing that to the real slice. So what you can see is we lose a bit in resolution. This is a harder task than maybe the last one, or it's different anyway. But we're capturing most of the important structures, and this is something we're actively working on to make better. We can also, here's a bit more detail looking at a particular feature that's important when you're interested in looking at CTs. For instance, looking at lung nodules, which you might use to diagnose various kinds of breathing disorders, and showing that we are getting a lot of this information correct by using this X-ray to CT reconstruction. So I'm going to move on from some of the applications to maybe some broader challenges that we've been working on to enable what we think of as the next generation of AI in healthcare. So modern AI depends on data. All of the results I've shown you so far depend on being able to look at medical data. However, one of the key issues that makes this challenging is that privacy is very important when you're dealing with health data, and you don't want to reveal any information about the patient. There are many good reasons for this. Today, I'm going to talk about two ways that we're trying to tackle getting the best of both worlds. So getting good AI models while still preserving, respecting privacy. We're going to talk about data synthesis and federated learning. So my first discussion is going to be on data synthesis. This is with colleagues at Georgia Tech, here at Illinois, and also at DuPage. So imagine, if you can, here are two X-ray images. One of these images is an X-ray from a real patient, and the other is a fully synthesized image that's the output of a model. So there is not a patient in the data set that has this X-ray. And I'll give maybe a quick pause if you want to guess which might be the real X-ray and which is a synthesized X-ray. So I'm not sure what you guessed, but the right answer is the real one is on the right and the synthesized one is on the left. And if you didn't get it right, maybe to get some solace, I'll mention that we asked the real radiologists to look at the images that we'd synthesized and gave them the same kind of test I just gave you to choose which was real and which was synthetic. And what we found is that more than 40% of the time, the synthesized image was selected as a real one. In fact, for a few of the radiologists, they selected the synthesized image much more often than the real one. The way that these kinds of models work is that we build generative models. So here the idea is that I give you a data set and you want to build some models such that I can, it captures the distribution of the data and I can sample from that model in order to get new data samples that look like the original data that you trained the model on. So here are a few more examples, again, more in X-rays. This works pretty well. Building on this work, we decided to push a bit further. Here I'm showing a block diagram of an extension to the earlier work where what we wanted to do was synthesize both the X-ray images and in addition, clinical notes. So if you look at the X-rays, often there'll be a discussion or a description of the major disorders and some other annotation on the X-ray after the radiologist is done analyzing the X-ray. And so we asked whether we could synthesize both the X-ray and the clinical notes. And I'm showing here some results. On the right, I'm showing a sample from the model versus the real sample. So the images, again, are close in terms of looking realistic. And the text measured in multiple ways also is realistic in terms of capturing the nature of what's in the image. So what we showed here, excuse me, on the left is a study with radiologists where we asked them to rank or rate 1 through 10 a set of results from the synthesis model. And what we found is the scores for the real data and the scores for the synthetic data were quite close, suggesting that they're both quite good at capturing the information. The synthetic data is quite good at capturing the information almost as well as the real data is. And so synthetic data, I think, is quite promising as a way to get around privacy issues and still get high fidelity data that we can then train machine learning models and AI models on. Another approach that we've been exploring to improve privacy in health AI is federated learning. And I'll briefly talk about some of this work, this in collaboration with OSF Healthcare and also colleagues at Illinois. So the idea of federated learning is instead of collecting data in a single place and having a model trained on collected data, maybe you can train models locally on, say, hospital data, but still get all the benefits you would have by centralizing your data by moving the models around. So if you like, instead of moving data to a centralized place so you can train an AI model, you instead move the models to the data. So the model acts on the data, and then you have some way of aggregating the models together. So this is an interesting, somewhat recent paradigm in how we think about training AI models. And we've been exploring how well these kinds of approaches work for medical applications of various kinds. So here, there are a bunch of, I think, quite interesting technical challenges that are different from challenges that one would have faced if you were dealing with standard centralized data. I wanted to talk about a little snippet of maybe an interesting challenge of thinking about security when you're training in this kind of distributed way. So one of the tools that we use to get the decentralized machine learning and AI models to train correctly is something known as secure multi-party computation. The idea is if I give you, if I have data at a set of different clients or different devices, and I'm interested in computing a function on all the data, is there a way to compute that function such that at the end of my operation, everyone learns the solution, so everyone learns the outputs of that function, but no one learns anything about any other individual's data or anything else about the system other than their personal data and then the eventual function computation. So this is an interesting set of problems. There's an entire area of security and cryptography that thinks about this. Maybe a little snippet of how one could use this is something like computing a sum of 3 values. So suppose that each of the different hospitals has 3 values and I want to compute the sum of them or the average. One thing that you could do is add noise of different types to each one of those inputs. So what I'm showing here is the original data x1 with noise in this blue triangle. And then I add the opposite noise, say to x2. I can do the same thing with x2. I can add 2 amounts of noise being opposite from x2 and x3. And I can do the same thing with x1, opposite noise, sorry, with x3, where I add noise that's opposite from x2 and then noise that's opposite from x1. Now, if the amount of noise is high enough, no one else, including the server or the individual workers, can tell anything about the data that was sent by any of the other devices. Yet the server can compute the correct average because all of the noise cancels out. So the idea is to send the right kinds of noise that can be computed in a cryptographically safe fashion, I apologize, such that the average is correct, even though you cannot tell the regional signals from each other. So this, I think, is a really interesting line of work that's at the intersection of machine learning and systems and also AI generally, and I think is among what we think of some of the future of building machine learning and AI systems that work well in healthcare applications that can both preserve privacy and get us a lot of the useful applications and the results that we've talked about earlier in the talk. I want to close out with another line of work thinking about explainability and trust in AI. So switching gears a bit, uh, trustworthiness is extremely important if you want usage of a system in critical settings like healthcare. And it's more and more important because even though the way that we build machine learning and AI systems are fairly simple in terms of the underlying building blocks, once combined, the combined models can be quite complex. And complex in a way that it's hard for a person to sort of look at a model and get a good sense of what the model did and why it's working like it's working. Now, there are many ways that you might care about interpretability and transparency in AI, particularly, say, for healthcare applications. So you might care because you want to debug your model and you want to know sort of how it's working in order to debug appropriately. For doctors and other healthcare professionals, they want to know when it's working and not working so they can build trust. For the rest of the population, for you and me, we're interested in making sure that if an AI system is replacing a human decision maker, its predictions are fair and non-discriminatory. And I think an interesting angle on this is actionable recourse. So if the model leads to a certain prediction, can I understand what I need to do in order to change the prediction of the model, which might give me something, some actionable changes I can make, for instance, if I'm using this in diagnosis setting. So I'll talk a little bit about this. This is work with colleagues in various places, including Google and University of Texas and Vector Institute. So here's an example. Suppose I have a model that predicts readmission. So I want to know if a patient will be readmitted next month. So I can measure a bunch of different attributes. I can construct features and then build a predictive model. And so if I applied this model and for a certain patient, say, here are the features of a certain patient, I can get a score for whether I think this patient is likely to be readmitted. However, I might be interested in what can I change about this model such that I change the outcome so this patient will not be readmitted. And so this is the idea of recourse. If any of you have ever gotten, say eye exams, or I think maybe a better example, if any of you have ever gotten credit reports, might be early for some of you, anywhere where you see, in addition to some score, you also see here are the things you can do to change your score. That's the idea of what Recourse is trying to capture. And so what I'm showing here is an example where the model says, or the procedure says, if I change these few things, I get a different outcome from the model. And you can imagine that this is useful both for understanding how the model is making its predictions, but it's also useful for debugging the model to figure out sort of exactly how the model is working, figure out if it's being equitable and fair, and many other, I think, useful applications of debugging machine learning models. So we have a system that we've built and we're exploring and building on to do this. It has some interesting components that uses generative models and constraint optimization. I think the key properties I think are interesting is that we look for recourse under the model that's feasible. So you want the model to suggest changes that actually are possible, that changes actually can be made by an individual. We're looking for the smallest set of changes that modify the outcome. And we also want the change to be realistic. So we want that the change that the model asks for looks like some real individual in the data, or some real individual that could have occurred in the data. So these are properties that we impose on top of just looking for the change in the data that would lead to a different outcome from the model, which leads to the approach that I talked about a second ago. So what I've tried to do today is outline briefly some applications of AI in healthcare, and also some broad challenges and early work that we're doing to try to address them, thinking about privacy and trustworthiness and AI broadly, and specifically AI for healthcare. In my lab, we have a variety of additional work that some of you might be interested in. So we think a lot about models for a variety of applications. I didn't talk a lot about things like risk scoring and comorbidities if you're building predictive models for health applications. We think a lot about evaluation. So how do I pick good measures that tell me whether my model is actually doing what I hope it's doing. I had a chance to go over some of the privacy and trustworthiness work that we're doing. We do a bit more thinking about interpretability, fairness, and robustness of models, and happy to cover some of these maybe at a later time. Thank you for your time. It was a pleasure covering these for you today.
Great, thank you, Professor Koyejo. We're going to move on to the Q&A session right now. One question that we had was, what criticisms or critiques exist within the application of this AI in healthcare, and how would you say that this application could become more trustworthy for both patients and medical professionals?
Yeah, so that's a quite tricky, I think, interesting problem, but it's definitely one that I think will have to be addressed if AI for healthcare is going to be sort of a reality at scale. So I think there are lots of open questions in terms of ensuring that when the model makes predictions that they're sensible. I think when we evaluate what the models are doing, they seem mostly right. But you can always imagine that the model can be applied to settings that are very different from what it was trained on. And sort of one of the dirty secrets of AI and machine learning is that most of the ways that we construct models work really well when the data is similar to what the model has seen before, but can break down in unexpected ways when the model is far from what it's seen before. So I think there's a lot of work to be done, some of which we're doing, some of which the community is thinking about, and ensuring that the models built behave reasonably or are able to defer to a human decision maker in places where they don't have a good sense of how to make sort of good decisions. I think there are interesting questions in the right way to augment human intelligence. I think the most useful versions of these are not replacements, but are meant to sort of help medical decision makers look for maybe places they may have missed or not thinking about, potential sources of issues, potential alternative hypotheses for diagnoses. I think those are some of the most interesting and maybe most useful applications of much of what I've talked about, particularly in the sort of diagnosis and treatment applications. So a lot of work I think still needs to be done in improving the trustworthiness and in interpretability and just general usefulness of AI models when applied to healthcare. But I think we're making useful steps that we hope will lead to good outcomes in the long term. One thing I should mention, I forgot earlier, AI systems, because of the nature of how quickly they can make predictions, are good at scaling things up. So they can make predictions very quickly, which means you can make a lot more predictions. One of the things that I think are clearer now than they were a few years ago is one consequence of this is if there's bias in the system for a variety of reasons. So if the system is unfair because maybe the way the data was collected or the way that the training occurred or some other source in the system, these things can be multiplied and get much worse when sort of pushed through an AI system. So I think also fairness in AI broadly is, again, I think a very important topic, an important topic both for the usefulness of these systems, but also ensuring that they are trustworthy. So they do what we want when applied, when used for healthcare decision-making settings.
Yeah, so one of the other questions we got was, are there any other other AI approaches that could be used for these kind of imaging problems, or any alternative methods that have been looked at but may not work as well?
Yeah, so a lot of these imaging questions are not completely new. There have been a variety of signal processing approaches and sort of approaches that some of them implemented, and actually some of them work pretty well in many settings. I think the promise and the power of AI methods is one, the ability to learn directly from data allows, I think it allows sort of possibilities that are harder in the general setting, because in the standard setting, you have to hand design algorithms for every single application. And sometimes that can be tricky. You can miss, I think, important cases because one has to hand tune things. So I think nominally, some of the signal processing approaches, one of the advantages the AI methods have off the bat is that because they are built to learn directly from data, they have sometimes advantages in flexibility to different settings. I mentioned already that there is a downside and that they don't always do the right thing when applied to data that's extremely different from what they've seen before. And I think that may be an advantage of some of the alternative methods because, again, they're typically built by intuition maybe, and sort of direct design as opposed to learning. And so you may be able to handle some corner cases using some of the classic methods. I think one of the emerging approaches that's most exciting, both in, say, imaging applications I've talked about here, but also things like control applications. If you think about all the way from, say, surgical robots all the way to, say, self-driving cars, is actually combining both of these methods and using them where they're best. So maybe using AI methods as good methods for sort of highly flexible decision making when the application or the target looks somewhat similar or is in the range of data that has been seen for training. And then knowing when you should fall back maybe to other approaches that may be hand designed or hand tuned, but are more robust potentially at the cost potentially of accuracy. I think one of the more exciting directions that AI is going is thinking not purely as a replacement even for alternative or existing methods, but thinking of how to combine AI methods with existing methods and, if you like, get the best of both worlds.
Great. I think one good question to kind of close off a Q&A on would be, for a student who is a bit younger, possibly in high school, what would you recommend, or how would you recommend they get involved if they are interested in this? And also going off on that, what technical versus medicine skills or interests would they have to have in order to do work like what you were doing?
Yeah, so that's a great question. I think one really good way to get involved in potentially some of these kinds of research is to, if you get in college, often classes will have projects that will look like some of these. I think that's maybe a low effort way to get into working on some of these kinds of projects. I think more and more, it's very exciting that many medical applications are now available as sort of public competitions. And I find that competitions can be a really good way to get practical, hands-on comfort with trying to solve some interesting applied problems. So I'm thinking of Kaggle competitions, for instance, as a way to try to develop methods that might solve some interesting medical tasks or scientific tasks or various applications like this. I would, as you move forward in your education, as you get a chance to maybe potentially do research with a lab or start talking to some of your colleagues and getting, I think, interesting ideas. I think there are always opportunities to collaborate. Again, some of the best work happens in collaboration with medical professionals for many great reasons. One, they know the area, they know the right problems to ask, they have the data available. So some of that is a bit harder as sort of individual, walking up to a hospital and saying, hey, I want to solve your medical problems. I think some of that can be eased in by working with labs as you move along in your education and further on in your career. In terms of skills that you need in order to do well, I think the biggest one is curiosity and sort of hard work, in my experience. I guess it's not really a skill, but I'll mention that because I think it makes a big difference. I think it's really hard to move the needle on doing interesting stuff unless you're motivated and put the effort in. And some of the motivation would just come from interest in thinking about these problems and interest in trying to solve them. Beyond that, I would say the programming skills that you're hopefully starting to develop and you'll build on as you go through university, or you build on maybe on your own, going through various kinds of coding exercises, are again the bedrock of everything. So underneath all this, machine learning sort of looks like statistics and probability and linear algebra, but to actually get things to work, you need to code things up. So luckily, I think machine learning, compared to many other fields, has a really good track record of having easy to use, easy to deploy software tools, to where you don't necessarily need to know the nitty-gritty of sort of how the components of things work. You just need to know sort of how to code enough to combine things together to actually do really, really useful applications. This is a good thing because I think it can ease getting into the area and ease playing with potentially new and interesting things very quickly. At some point, I think it can be extremely useful to actually understand what's going on under the hood, because this lets you troubleshoot problems a little bit better, helps you develop new ways of solving problems when existing tools don't fit the problems that you're looking to solve. And so some of this you'll learn in classes as you go along. I think the key technical tools beyond implementation would be, again, I've mentioned linear algebra and probability show up a ton. A bit of algorithms, but I think by far in modern machine learning and AI, various flavors of sort of probability and linear algebra, the bedrock of how we think about most ways of building machine learning and AI systems. And so comfort with that will probably serve you well as you think about these topics and are sort of building your skills and building your thinking about the areas that you want to sort of spend time on or look interesting to you. Beyond I think, again, these are maybe the key areas to build on. So both foundations, which is interest and hard work, coding, so you can implement things, you may be using existing tools, and then eventually the mathematical tools so that you're comfortable building your own, and understanding what's going on and how these systems work, I think are sort of some of the main, the core things that you need to know to be successful in this area.
Thank you. And thank you so much, Professor Koyejo, for talking to us today. It's extremely important to understand how AI and technology like that can be used in application, real world application like in AI. So thank you very much. And thank you for coming.
Yeah, it was a pleasure. Thank you for having me.